All right, so good evening, everyone. Thank you for being with us tonight. I am Jonas Beltran, and together with my mates William Revilla and Joleil Villena, we will present our capstone project entitled Forecasting the Power Demand of the Luzon Electrical Grid using Clustering and Predictive Modeling. So let me paint you a picture on our motivation for this project. Last March 2019, next slide, please. The grid was operating in such low reserves that there's only a 624 megawatt difference between power supply and demand. And in fact, the average power supply and demand throughout the whole of 2019 had a difference of approximately 1,000 megawatts only, which is dangerously close and threatens our energy security. Thus, our study is significant now, since forecasting power demands not only serve as a foundation in the planning and construction of infrastructure for additional power generation, it also establishes our energy security. In addition, it is a good indicator of our economic growth. So for our first objective in this study, we need to gather the data from the website of the Independent Electricity Market Operator of the Philippines. And next, when we had this on hand, we needed to perform an exploratory data analysis to clean the data set and formulate general insights from it. Clustering proceeded next, and for this, we used multi-layered clustering algorithms to determine the most sensible combination of resources that belong in different sectors. And lastly, time series forecasting models were applied to the cluster data to determine future power demand, both in total for the Luzon grid and the different sectors. Our tools that we used to accomplish this were Python, Jupyter Notebooks, stats models, and Facebook Profit. So for our EDA process, here is Joleil.
So we started with almost 5 million entries of data on 264 resources from Luzon and Visayas. A resource is the interconnection point between entities such as power suppliers and consumers and the electrical grid within a local area. We then narrowed it down to Luzon data with only 2.4 million entries on 183 resources. We cleaned our data mainly by removing duplicates and by setting a threshold of 5 megawatts of total power demand in order to eliminate those resources with low total demand throughout the dataset. So we first looked at the historical total daily power demand of the Luzon grid. An electrical grid is where producers send electricity to their customers. Looking at this chart, we saw intuitive trends like how we consume more electricity during months with higher temperatures and vice versa. We also noticed the effects of specific events such as power outages and holidays, but the largest influence on our data came from the effects of the quarantine brought about by the pandemic. Comparing power demand on the per hour basis, we verified that on average, power demand decreased during all hours of the day, especially during office hours. This is attributable to the closing of offices and public places. Analyzing more granular data, we noticed that the behavior of resources vary. And as seen on the charts on the left, these peculiarities are washed out when looking at Luzon as a whole. We were then able to see patterns in resources and noticed similarities among them. This will be further discussed by Jonas in clustering.
All right. So after our EDA process, we subjected the data to another round of pre-processing to normalize the median megawatt value per resource per hour. So this resulted to our database to have our number of sources to drop to 153 from 183. This was done in order to focus on the daily movement of the power demand of each resource instead of its magnitude. Clustering algorithms were then used to segregate the resources into their sectors, with hierarchical agglomerative clustering yielding the most sensible results. The output of this process was a total of 6 distinct clusters. And next slide, please. The residential sector included 59 resources with an average of around 26,000 megawatts power demand in between them. And the next one had 17 resources, and these belonged to various sectors. And they had an average of 5,800 megawatt demand. The commercial sector had 59 resources as well, but took the huge bulk of the demand at around 153,000 megawatts. And the power generation units had 6 resources and an average of 4,400 megawatt demand. And for the industrial sector, next slide please, they had 3 resources and an average demand of 880 megawatts. And lastly, another commercial sector had been detected, having 9 resources with an average demand of 4,200 megawatts. The main difference of this one from the first one is that the activities for this particular cluster are more pronounced in the evening, suggesting that they must have been commercial offices working during the graveyard shift. So the following figures show the average total demand per day for each of the determined sectors. And now we will proceed into forecasting, and here
Okay, so now we can proceed to forecasting. To illustrate, this is the time series data of the daily power demand of the Luzon grid of the 153 resources that we considered. Next, please. The first model that we ran was ARIMA. It is generally an acronym that stands for Autoregressive Integrated Moving Average. And here we ran it on the 6 clusters that we have identified. And as you can see, it roughly forecasted a straight line. Next. We again ran the model for the Luzon grid where it showed a similar behavior where it again forecasted an almost straight line, and we'll also get into why that happens later. Next. So now knowing that ARIMA did not work, we tried a different model called the FB profit model. Here we ran it on the 6 clusters. And if you look at it visually, the forecast period roughly follows the same shape compared to the same period of last year. Next. And as you can see, looking at the 6 cluster, the sudden drop and sudden spike when lockdown was implemented and when it was lifted produced a forecast where it skyrocketed. Next. So now we look at the forecast data when we sum all of the results of the forecast from the previous slide. Next. So here we see the results when we run the FB profit model for the total daily power demand of the Luzon grid. Both of their forecast periods shows a roughly similar shape compared to the same period of last year and roughly the same values. So now we go on to the model overview. To roughly answer why ARIMA forecasted a straight line, it's because a time series data that has a weak seasonality would often result a straight line forecast. And our data not being stationary where the mean, variance, and autocorrelation structure changes a lot over time, and this is evident on the sudden spikes and drops that shows no patterns over the dataset. FB Profit, on the other hand, considers the trends, seasonality, cyclic patterns, and even irregularities in our data. It works well with missing data and flexible with sudden dips or spikes in the data, which is why it worked better than ARIMA. Next. So to conclude our results, the Luzon electrical power grid forecast suggests that electricity demand is normalizing, but a 4% increase is observed in demand. Next. And for the 5 clusters, for the forecast of the 5 clusters suggests that their respective sectors are normalizing, and the 6th cluster that we have identified show the forecast behavior where it just continues to rise since that cluster is identified as a commercial sector where night shifts are prominent. The sudden drop and sudden spike during the lockdown and when it was lifted caused the model to predict its future values to continue to increase and has not normalized. Next. So some recommendations that we can do is to increase our historical data. A longer data set is always going to help with forecasting, and improvement of the models through K-fold and other validation methods will allow us to select better model dynamics. Another thing we can consider for the FB profit model is incorporate special holidays or events in the forecasting since it could take those into consideration when encoded. And on future studies, we could incorporate the supply side of things to see if our industries could actually keep up with the demand. Next. So to end this presentation of ours, here are our insights on what we could start supporting when it comes to energy, such as a call for better infrastructure to prevent power outages and meet our current and future demands. Stakeholders could also invest in renewable energy. Next. And for our roles as a citizen, we could always avoid the use of unnecessary electricity usage since we often take it for granted, not knowing that our demand is starting to catch up with our supply. And for those who can, we encourage everyone to invest in renewable energy systems to power their needs. And for everyone who wants to learn more about the process we did to this study, we will release a full documentation soon, and you may contact us through our LinkedIn profiles here. So thank you, everyone. We are now open to answer your questions.